We're going to wrap up this story now, telling about how we finally get the solar system into looking like what it does today. At a certain point, after that protosun has had lots and lots of gas fall down into it, it keeps collapsing and collapsing down until the energy builds up in the core to the point where hydrogen fusion is going to begin. And when hydrogen fusion begins, that's when a protosun ignites and becomes an actual star. Stars have a big hot fusion engine in the middle of them, which makes them very hot, very bright, and now you're going to be creating an even hotter, brighter object in the center, which is going to have lots of light radiation and lots of stronger solar wind that's coming out of it. And if there's any solar system gas still rotating around in here, that solar wind now is much stronger and is going to start to push it out of the solar system, way out there beyond the orbit of Neptune, where we know that we have comets hanging out in the Kuiper belt. So the comets are going to be out there with lots of gas, which will condense nicely onto their cold surfaces and make them into dirty snowballs. There are still leftover planetesimals that can be in your solar system, and they might get their little orbits disturbed when they come near a big planet and go swinging into the sun, get burned up, but they can also go swinging around the solar system in random orbits that make them hit planets and make them hit moons, and that can make lots of craters. So we see lots of craters on our moons and on our planets like the terrestrial planets, and we know that this is because of wandering planetesimals that still had to be cleaned up somehow and still had to go through a collision process even after the planets had mostly formed. But what about that asteroid belt that still has a bunch of pieces going between Jupiter and Mars? Asteroids never did form into a planet. They are leftover planetesimals that did not succeed in coming together to form a planet. So because of this, it is interesting to go out and study asteroids, because if you're looking at an asteroid, you're looking at something that's left over from the process of forming our solar system. And that's a good thing to tell you information about our solar system formation process. If we need to fill in some details in this theory, it can come from studying the asteroids. Now, the dramatic conclusion to all of this. We have a theory of how the solar system formed. What do you want to do when you've formed a theory? You want to have confidence in it. And you get that confidence by always testing the theory, going out to make more observations and checking to see if those observations fit with your theory. So, could we actually see somewhere where there are solar nebulas that are being formed so that we can check to see if it looks like what we expect from our solar system origin theory? And what we've got here in this picture is an actual solar nebula in progress. So yes, we do have this fantastic piece of evidence right here that tells us our solar system origin idea works. What we've had up to this point are drawings by artists of what they thought it should look like. This is not a drawing. This is an actual photograph of a solar nebula out in space that is in the process of forming, and it has the rings in it like we expected to see where planets should be forming and sweeping out the gases and the dust. How did we get this fantastic picture, which should have received a lot more attention in the news than I thought it did? We had to do this with very high resolution. And I told you before, you can get better resolution with telescopes if you get the telescopes to work in cooperation with each other through a trick called interferometry that also then uses computer processing to combine the light and information from the telescopes and combine it so you can figure out pixel by pixel how to fill in your picture with better resolution. So there is a set of radio telescopes, 66 radio dishes set up in the desert called the ALMA telescope, and that is spreads out its radio dishes over 15 kilometers apart. This gives incredible resolution for taking pictures of things in outer space. Resolution of 35 milliarcseconds. Now remember, an arcsecond is 3,000, it takes 3,600 arcseconds to make 1 degree. So an arcsecond is already a very small part of the sky. And this is 35 milliarcseconds. So it's thousandths of arcseconds in the sky. Very small patches of sky. So we have incredible resolution with this ALMA telescope array, and we're able to zoom in on this and see a proto-sun that's trying to form in the middle of a big rotating gas and dust nebula, just like we talked about in our theory. This star that we pointed ALMA at is called HL Tauri, because when you go down the list of all the stars in Taurus, then you're going to go through the Greek alphabet, and then you're going to have to start another naming system, and you get all the way down to using double letters like H and L when you get to this point of light that we saw in space and said, let's take a look at that with this ALMA telescope. And what we saw as a point of light was the light that was coming from a large spread out solar nebula with a proto-sun that's forming in the middle and has not become a star yet. This is a pre-main sequence star. It has not yet gone from protostar stage to becoming a main sequence star. So, in the looking at this photo, scientists have determined that the process here for the solar nebula formation has to make this thing less than 1 million years old. And remember, our solar system is 4.5 billion years old to look the way it does now. So this is a very young formation in progress. But now look at the gaps. These are the gaps where we said we should have planets forming that start to collect all of the gas and dust as they go around in orbit. And you've got a ring there and another one out there, and then more of them out here and even more of them out here. Through their understanding of how far away this nebula is, 450 light years away, and how big across it is, they can figure out the size of this solar nebula. And this innermost gap is like 20 to 30 astronomical units. So, where would that put it in relationship to our solar system? Well, what's 30 astronomical units away from our sun? Neptune, the edge of our solar system. So this ring right here, if we compared it to our solar system would all fit inside the very first ring, meaning that this first ring, still with its gas and dust that we see as a blob in the middle, still has a chance of other planets being able to form between the ring right here and the center where the sun is eventually going to appear someday when it becomes an actual star. All right, so that means our entire solar system fits in this ring. What would this be for our solar system? This would be something big out in our Kuiper belt, something out there around 70 astronomical units away. We haven't seen anything that big in our Kuiper belt yet. And what are these? Even further out, and more rings even further out. If these formed large planets, and this was like our solar system, things way out here would not be getting lit up very much from a sun that's so far away. It would be extremely hard to see them in telescopes. So could we already have something that's formed all the way around our solar system with larger planets way out there, and we don't know that they're out there because they're too hard to see? Makes you think, what else could be out there to discover even in our solar system? And it's because we can look at something like this that we can wonder about that. Now do you understand why we should keep pointing telescopes out there in space to look at things that we haven't looked at before?